All right. So microphones on this end look like they're working okay. Let me check the output on this end. If I could get a bit of.
Good morning.
Yay, there we go. All right. So that looks like I'm coming out of the computer right now. Let's see if I can get you into the fancier speakers in the room. Could we try good morning just one more time?
Good morning.
Nothing out of those. Darn. All right. 1 second here. Fiddle with this thing. And it says it's working, but it's lies. So we're going to switch you back to the computer output. That will be okay. I'll crank it way up. Speakers. Maybe just for gits and shiggles. Let's try. Could we get another good morning real quick?
Good morning. It's possible that the other speakers just aren't set to be the speakers for that computer, and that the current speakers hooked up to it are set as the default speakers, and that might be why they're not working. So the speakers themselves may work, but aren't being asked to be used by the computer.
It looks like I was selecting the wrong ones. Yeah, but I think we're Gucci now. It looks like you're coming through the fancy speakers in the room, and the display at the front. The only thing that I have not done yet, we're still unzipping the files here. So how did we want to run through this? What was the actual are the lectures completely pre-recorded, Sarah, or was this something like
what you have
over?
So those are completely pre-recorded. What you have are videos. That's why they were put in zip files, because they're kind of massive when they're not.
I saw that. Yeah. Okay. Very nice then. What I will do then is I'll just kind of DJ from up here, and I'll let you field questions through Zoom. I'm going to dim the lights at the front.
Sounds good.
And then in order for folks at home to get this, probably best for me to screen share rather than relying on like the camera's take on what is up front here. So let me do the title card thing.
Yeah, they should work perfectly well for screen share.
Sorry,
the only thing, the files should work perfectly for a screen share.
Good, okay. So today, Sarah is going to student teach section 7.2. Which is on trig integrals, integrals of trig functions, which is called trig integrals. And I've looked through her notes, they're excellent. So I don't think you guys will have any problems learning the material from them. Before we dive in, there's just one thing I want to say that the textbook doesn't say and Sarah's notes don't say, because the textbook doesn't say it. It's that not pretty much, truthfully, any combination of trig functions can be broken down into integrals of the type we're going to see today. So if you have, products and sums and fractions made up of the 6 standard trig functions, they can all be expanded, factored, simplified using definitions and trig identities into integrals of the form we're going to see today. So even though it might not seem like it, because we're going to look at, powers of sine and powers of cosine, powers of secant and powers of tangent multiplied, that really is everything, with the one exception that you sometimes have to swap in co-functions, right? So like integrals with powers of cosecant times powers of cotangent work the same as integrals of powers of secant and tangent. So just be mindful of that as you run through this, because some of the homework is going to have problems that may appear to be outside this scheme, but are not. You just apply the same rules to the co-functions. All right, I think that's it. Oh, one more thing. Later in the semester, remember the content difference between this class and the non-honors class is Fourier series, right? We're going to talk about Fourier series in this class. This shit, hugely important for Fourier series. So be mindful of that. This is one of those topics that's going to come back in a big way a little later. All right, so I am going to, it's like VLC's never been used on this.
Good morning, guys.
Pause it for a second, turn on the screen share so everybody at home can see. Maybe I should queue up the other ones. Nah, we'll just. All right, here we go. You guys can see if they're okay. Speakers here.
Yeah.
Oh, let me do the me share the audio. To do that. Yeah, sound. All right, here we go.
Doing trig integrals, which really is we're going to be using some of our good old trig knowledge to take U sub to the next level in some areas where it would otherwise really fail with certain trig terms inside of an integral. So I always like to start with why we're bothering to do what we're about to do, not necessarily from a frumpy, so then why should I do it standpoint, but from a, it just sort of guides my steps in a way. So this is why. Oh, we went back a slide. Here we go. So why is this necessary? So let's look at this classic example right here. The integral of cosine cubed x dx. So we're going to attempt a classic U sub, as you can see. U equals cosine x, and then du equals negative sine x dx. But there's a problem. There's no sine x piece to pair with our du so that it can replace dx. So U sub hasn't solved anything because we still have x terms, and we can't have an integral that has both x and u terms left after the U sub is complete. So our current U sub skills are creating a catch-22, where there will always be an x term left hanging around. So clearly we can't solve this based on our current capabilities with U sub. So that is why we're doing this. And I'll give you a couple of seconds to write.
I'm going to try that.
So, how do we do this? Well, we'll start with the simpler ones, the sine and cosine trig integrals. So to do this, we'll be bringing in an old trig skill set. So if you haven't done your trig identities in a while, I recommend hopping in there. There's probably in our module, I'm going to assume somewhere, Professor Faustigger probably actually had some stuff, and then also you can just, I always just run a quick Google search when I need to review these because people have put up so many different charts of trig identities up online. So if you just want to brush those up, I recommend it. So, trig identities. So we'll specify which ones we're going to be using as we go along, because we won't be necessarily using all of them. So let's start with this classic sine squared x plus cosine squared x equals 1, and we'll generally be using it in these rearranged form. Cosine squared x equals 1 minus sine squared x, and sine squared x equals 1 minus cosine squared x, because we will be replacing one with the other. So let us illustrate with an example after a few seconds for you to write this down. So let's try that above example again. So note the substitution of the equivalent expression from the trig identity, because you're going to see these, I'm going to do these throughout, just sort of highlighted in yellow so that you can sort of follow where it's going. And blue is usually where I'm highlighting where the U sub has taken place. The yellow is usually where a trig identity is taking, like a trig identity replacement is taking place. And there's might be one or two other colors, but we'll see as we go along. So let's run it again. The integral of cosine cubed x dx. So integral of cosine cubed x dx, the first thing we do is we split it into two pieces. So we have a single cosine x and take this cosine squared x on its own. And you can see immediately how we're going to replace this and how this avails itself for U sub. So quick U sub commercial break. We'll be back after these important messages. So U equals sine x, du equals cosine x dx, and it just matches gorgeously. So here we go, we're back, and we've done our U sub. So we have a 1 minus u squared du equals, just we get our brackets. Don't forget the plus c for your indefinite integrals. So we have a u minus 1/3 u cubed plus c equals sine x minus 1/3. This is essentially where we're just taking our u, putting our u equals sine x. So we're popping that right back in so we have our final answer. Don't forget to do that either. So sine x minus 1/3 sine cubed x plus c. That's our final answer. And you can see how once we just replace that out, U sub goes super smoothly. And that is officially why we're taking U sub a step further, because it's clearly just really solved this one. So I'm going to give you a couple seconds to just write all the stuff down.
We look at cos cubed.
But wait, there's more. So there is another trig identity we'll be using for some of these. For integrals where sine squared x plus cosine squared x equals 1 does not do the trick. And that is the half angle identities. Now there are two different forms that you tend to see half angle identities in. There's one where it's the sine theta over 2. We're using the other type. So this is where it is. So we have sine squared theta equals 1 minus cosine 2 theta over 2, and then cosine squared theta equals 1 plus cosine 2 theta over 2. And we'll generally be using it, we will be generally replacing the theta with x, because if you think about integrals, you don't often see integrals where it's an integral with thetas inside of it. And then we will be pulling out, because there's essentially, you could technically see this as a parentheses right here, and there's a 1. So there's technically just a 1/2 fraction in each of these, and we will often be pulling those out right at the beginning and essentially doing this as our identity that we'll be replacing. Not in every case, you'll see, but generally. There's also one, and it's not written here, but it might occasionally be used, where it's sine x times cosine x equals 1/2 sine of 2x. I haven't come across or seen it used yet, but yeah, that is not impossible. I'll repeat it again in case you're writing that one down. So it's sine x times cosine x equals 1/2 times sine of 2x. And I will give you some time to write. Sorry for that thumping noise. My phone has my notes on it, and it keeps falling over. So, as usual, I find illustrating with an example it just shows me how things are being used in action. So here's our example, and this is a definite integral. So don't forget the rules associated with the definite integrals will come later. So we are doing the definite integral from 0 to pi of sine squared x. So attempting to apply our previous sine squared x equals 1 minus cosine squared x won't help here. We'll just end up back in that catch-22 that we kind of started with when we were looking at cosine cubed x, where we don't have anything to match with our dx. Oh, I forgot a dx. Do not forget a dx when you write these. Where there's nothing to match our dx so that we can fully finish out the problem. So you can see it showed up over here, but yes, that's my bad. So we will use half angle identities, because then we can solve it. So the definite integral from 0 to pi of sine squared x, little dx right there, equals 1/2, and you can see because 1/2 is an independent variable here, so you can pop that right out, and we have. So 1/2 of the integral from 0 to pi of 1 minus cosine 2x, and you see we've just literally just done that quick replacement there, dx equals 1/2, still outside, x minus negative 1/2 sine of 2x from 0 to pi, and that equals 1/2 times pi minus 1/2 sine 2 pi minus 0 minus 1/2 sine of 0, and all that comes together to equal 1/2 pi. And the green highlighting here, you'll see in a second why I highlighted that. There is a micro u sub that takes place there. And I'll break it down in the next slide, in case you were wondering, because when you're getting the integral of, when you're getting an integral of when there's a 2x in here, there's a micro u sub that takes place. I actually just highlighted it in the wrong spot because the micro u sub happens right here. So I'll just give you a couple of minutes to write that down, and then we'll break down that micro u sub in case it floated by one of you and you were wondering what to do when there is a 2x in here instead of a regular x. At this point we've come across it a couple of times, but just in case. So the micro u sub, which actually took place here, not here, but here it is. So we're looking at 1/2 times the definite integral from 0 to pi of 1 minus cosine 2x dx. And what we're doing essentially is we're splitting it into two pieces. So we have 1/2 still outside there. So the definite integral from 0 to pi of 1 dx, which just becomes x. And then this is the trickier bit because there's a 2x in here. So cosine 2x, so we do a micro use of u equals 2x right here, du equals 2 dx, and 1/2 du equals dx. And so we have we just end up with this extra 1/2. So cosine becomes sine, and it's the minus stays because sine is positive, like cosine to sine, you get positive sine. And then you just get this extra 1/2 in front of sine because of that 2x. And then just from there it goes, you know, business as usual through the rest of that problem. So I'll give you a couple seconds to write that down in case you wanted that note. But you're going to come across a lot of micro u sub in trig integrals, or at least I did. So it seems likely. I'll give you a couple seconds.
Do you not need to change the bound function as well?
I think you can usually get the end derivative fast enough that I would argue you don't need to write it. So if you can tell me that the integral of cos 2x is 1/2 sine 2x without like writing out the steps, then you don't need to change that. That's kind of rough.
So there are even going to be occasions where an identity will be applied more than once. So you'll break down a problem to a certain extent, and then you'll get another chunk where you can replace a piece with an identity all over again. So let us look at an example of that. So the indefinite integral of sine x to the 4th dx. So what we first do is we're going to essentially, because sine of x to the 4th can be broken down into sine squared x, all of it squared. So that's what we're doing here, and then we see this lovely little bit that we recognize right there. We are going to sub in a half angle identity, and it equals 1 minus cosine 2x over 2. And don't forget that it is all still squared. And notice we did not bring out the half right away. We can't, because since this whole expression here is squared, that what would otherwise be an independent variable, that half that we could bring outside, is still kind of stuck with this chunk here. So we have to first apply this, distribute this squared right here, and then we can start bringing things out. And it will become a 1/4 in that time. So we'll get to that in just a moment, but first I'll let you write that down. And then we'll work through the whole problem. The nicest thing that you can do for yourself is just kind of keep in mind when you see something like this, what can I break this into so that identities will be useful? And once we're done with these examples, we're gonna come up on just the basic sort of standard rules, what to look for that will tell you kind of generally what you should do with it. Moving right along, so here we go, this is where we left off. So this is squared dx equals 1/4, because now this became the 1/2, not this, there's a 1 that's kind of times all of this, and so that 1/2 becomes 1/4 because it got squared. And so now we have 1/4, and you can pop it out of the indefinite integral of 1 minus 2 cosine 2x plus cosine squared 2x dx, because that's how we did, once you square the top, because don't forget this isn't going to be like 1 minus cosine squared 2x, it's going to be 1 minus cosine 2x times 1 minus cosine 2x, and that's what you're going to get. And if you look here, there's another cosine squared, and it's not regular x, but it's a cosine squared item here, and we can apply an additional half angle identity. But keep in mind that that is not cosine squared x, that is a cosine squared 2x, and that will, the half angle identity will be further modified here because of the 2. We have to apply it correctly. So cosine squared 2x equals 1/2, 1 plus cosine 2 times 2x, so it's essentially
1/2 times 1 plus cosine 4x. So that becomes like our new modified half angle identity. So we're going to pop that in right here. So you get 1/4, that's still out there, times the indefinite integral of 1 minus 2 cosine 2x plus cosine squared 2x dx, and we're doing our substitution now. 1/4 times the indefinite integral of 1 minus 2 cosine 2x plus, and here it is, 1/2 times 1 plus cosine 4x dx. And we will get to the solution momentarily, but first I want to give you a chance to write down all of those numbers.
And I think Sara's done a good job explaining this. I do want to pause just for a second because I know this is a sticking point. Just to show. So I think sometimes it's just easier to see the identity. The half angle identities that we're using. Sine squared theta equals 1/2 times 1 minus cos 2 theta, and cos squared theta equals 1/2 times 1 plus cos 2 theta. If in the second one, you replace theta everywhere by 2x, we get the modified version that she has. So if I plug in a 2x here, which is what I need, because I've got a cos squared of 2x, then I also need to plug in 2x here. That becomes cos squared of 2x equals 1/2 times 1 plus cosine of 2 times 2x. And I know it's literally the same thing she has on the board there, but I just wanted to have you see it actually plugging into the identities that we're used to. So these are the identities that we generally whip out when we have even powers of sine and cosine and nothing else. Since in that last integral there we have a cos squared of 2x, we would handle it the same way we'd handle cos squared of x. But the problem is my inside isn't just x. But you can always do this in any identity. You can plug in for that variable whatever you want. That's what an identity is. And it doesn't just mean you can plug in numbers, you can plug in other expressions. So here for theta, instead of plugging like pi over 6 or whatever, like you would in trig class to find some answer, we plug in 2x. And that gives us a new trig identity for the third part of that integral.
Because there's going to be some micro u sub, and we'll break it down a little bit. So here's our solution, equals 1/4 indefinite integral 3 minus 2 cosine 2x plus 1/2 cosine 4x dx. And you're going to see here the final answer equals 1/4 times 3 over 2x minus sine of 2x plus 1/8 sine of 4x plus c. And so note the micro use of that took place. So you can do this micro use of manually each time like we did the first time around. But for half angles, these are the ones you're going to classically see. You're going to see like a sine of 2x because that's just a classic half angle substitution. You're going to end up with a indefinite integral of sine 2x floating around somewhere. And you're going to get 1/2 cosine 2x plus c. And for a cosine 2x, you're going to get a 1/2 sine 2x plus c. And if you'll notice here as well, and conversely, when we bring our modified cosine squared 2x, you get a 1/2 1 plus cosine 4x. So if you're noting a pattern here, that's not an accident. So, but yeah, you can also, until you get very comfortable with those, you can literally just do that u sub every single time where you're going to pull this out, turn it into a u, and then work through like a quick tiny little u sub, and you're going to start seeing a pattern very, very quickly. So I'll let you write this down.
if I'm being finicky, and I hate to do this, the sine 2x integral here, I think this one should be negative. Sine 2x would be negative 1/2 cos 2x. Because the u sub u equals 2x would turn this into 1/2 integral sine u du, and then the integral of sine u is negative cos u. But this is the vibe. So we're always, you're going to see integrals sine of ax or cosine of ax all the time. And the little substitution u equals ax, we want to run those like quick in our head. We don't want to have to actually take the time to do them.
And we are going to come back with those basic rules
Thank you.
in the next video.
So these identities all important. I'll leave them up here, and at the end we'll have a table of identities. Okay.
So you say those are like the main ones we use, or?
I am going to add to those, but those, and she's going to explain in the next video. Under certain circumstances, we always use these.
Okay.
And the more general results, though, the 2 micro u subs that we use all the time are for these integrals. And this is what they come out to. So it's something you don't want to have to write those out every time, right? Every problem is going to have like 2 or 3 of those. But it really is just like u equals ax. Okay, so du is a dx. So 1 over a dx is du. So 1 over a comes out, and then this will become the integral of sine u du, which is negative cos u, negative cosine, and go back and forth. So yeah, you don't want to have to waste time writing those out. Let's go to the next video.
All right, welcome back. So here we're just going to summarize really quickly kind of what we've been doing with all of our different examples. So the overall skill we're adding to our u sub arsenal with trig integrals here is that we are using trig identities to rewrite trig integrals into a form where we can then use u sub to solve them. And which identity we use is based on whether the power of sine or cosine is even or odd. I'm not sure if you noticed that as we were going through our examples, but you're about to see there's a format there. So I'll give you a couple seconds to write that down. So there's our format. Definite integral sine of x to the m times cosine x to the n dx. So if m or n, these exponents, is odd, we're using this one, the cosine squared x equals 1 minus sine 2x, or if it's a sine, sine squared x equals 1 minus cosine squared x. If n is odd, we save one cosine factor and use sine squared x equals 1 minus cosine squared x to get all remaining factors in terms of sine. So say it was, so remember what we did with the indefinite integral of cosine cubed x, and how the first thing we did was split it into a cosine squared x times cosine, and then we left that cosine x and the dx, that was going to become the u sub, and then that cosine squared x, we turned it into a factor in terms of sine. So that's literally what it's saying. And then if m is odd, this one right here, save one sine factor. It's literally the same, it's just backwards. Save one sine factor and use cosine squared x equals 1 minus sine squared x to get all remaining factors in terms of cosine. Then integrate using u sub. So if you see that they are odd, it becomes a very nice, clear, very clean solution. So I'll give you a couple seconds to write that down. And then we'll get to if they are even. I have a feeling at this point you can probably guess what we do if they're even, but still, we're going to do it formally.
If you have enough time.
So, if they're even, if m and n are both even, use the half angle. So sine squared x equals 1/2, and you see I've pulled the 1/2 out here. Just generally speaking, that is often how you use it. Just be cautious, because if at any point this whole thing happens to be squared, or anything else that will make this stuck to this, and both of them sort of tied to this x and unable to be pulled out, you're going to have to distribute whatever it is they're attached to before you can pull the 1/2 out. But often you'll be able to pull that 1/2 out, it becomes an independent factor. But moving right along. So if they're both even, use sine squared x equals 1/2 times 1 minus cosine 2x, or cosine squared x equals 1/2 1 plus cosine 2x. So, yeah, very useful. So I always like to illustrate with examples. Now that we know our format, let's review it. So here's a solid example. Indefinite integral of sine cubed x times cosine squared x dx. So the power of sine is odd, so we set aside one factor of sine. So we've literally just split sine in half. So we have sine cubed x cosine squared x dx equals sine squared x cosine squared x, and then this sine x we've pulled out of there, sine x dx. And you can see where I'm eyeing the u sub, I've highlighted that in blue. And then we convert all other factors so that everything that's left is in terms of cosine. So we had sine squared x times cosine squared x times sine x dx, and we're getting everything in terms of cosine, so we get the indefinite integral of 1 minus cosine squared x, that's where we've done our substitution, times cosine squared x, sine x dx, equals, and then we're just distributing this. So indefinite integral of cosine squared x minus cosine x to the 4th times sine x dx. Quick break for u sub. So u equals cosine x, du equals negative sine x dx. Don't forget that that is a negative x, because right now what we're doing is we are differentiating, we are not integrating.
Quick pause for notation. Around cosine squared minus cosine to the 4 here, we need parentheses. So this sine of x that we grabbed off to the side, and so I highlight there because we're saving him for the u sub. He's going to be our du. He's multiplying everything here. And when you distribute this cosine squared across this parenthetical, 1 minus cos squared, you get cos squared minus cos to the 4th. That's perfect. But the sine x is still multiplying all of that. So we want big parentheses here around cos squared minus cos to the 4. In other words, that sine x is not just stuck to the cos to the 4th. Yeah, no, you're good. I think everybody would see it. Just want to make sure.
I honestly hadn't seen it, so I really appreciate that.
No worries.
So just something that I get confused at very often. So, and then we'll move on to the final answer, but I'm gonna give you a couple seconds to write this down first. So that's we've left off right at the u sub, and you can probably start putting together where this is going already, but we'll walk through it.
So before Sarah wraps this up, does anybody have a question or anything about how we get to this last integral here? This is a kind of classic or archetypal problem. This is about what you'd expect to see on a test. Feel nice and comfy. And we understand the game, right? The game is to grab whatever you need off to the side for your substitution, and then rewrite using trig identities everything else so that you can employ that substitution. So when we see the odd power of sine, I'm like, ooh, I'll grab one of those. And then everything else will be even powered, so everything else can be turned into cosines.
So we've done our u sub, and I left that right up here. So our u equals cosine x du equals negative sine x dx. So it's just beautiful. So this is where we left off before our u sub. So indefinite integral of cosine squared x minus cosine x to the 4th sine x dx equals, and don't forget that negative, be very careful with negatives and with constants in general. So negative indefinite integral of u squared minus u to the 4th du, because it just beautifully grabbed that, equals, and now we're going to integrate, negative 1/3 u cubed minus 1/5 u to the 5th plus c, don't forget that plus c, equals, and then this is where we're just, don't forget this last step here, where you're going to put your original stuff back in for u. So our final answer, negative 1/3 cosine cubed x plus 1/5 cosine x to the 5th plus c. And it just really takes everything about it that wasn't working and makes it work so beautifully. So I'll give you a little bit to write that down.
Same note as before, parentheses around cos squared minus cos to the 4, parentheses around u squared minus u to the 4. So this line here, paren there and there. And this line here, paren here. This is perfect. And then from this second to last line, she did two things. Distributed this negative and plugged back in for u. So that's why this became positive.
And let's take a look at an example of what to do if m or n is even. So the indefinite integral of sine squared x dx, and we're going to be using our half angle identities. Sine squared x dx equals 1/2, pulling that one out. 1 minus cosine 2x dx equals 1/2 x minus 1/2 sine 2x plus c. And did you spot the u sub this time, the micro u sub? I'll give you a couple seconds to write it down and point it out to yourself before I point it out to you. And it won't get its own slide this time. We're past that. But wait, there's still more. And I know that's more of a QVC, but it always makes me think of Price is Right. So we're going to get to that in the next video.
All right. So any questions on those examples? Notation, strategy?
Alrighty, welcome back. So we are going to take our skills yet a step farther, and also not really. It's a very similar concept, but instead of sines and cosines, we're going to be working with tangents and secants. This is a slightly new format. So we'll be using this trig identity, secant squared x equals 1 plus tangent squared x, and then this, which is literally a rearranged version of this. So tangent squared x equals secant squared x minus 1, as well as keeping in mind the derivatives for secant and tangent, which play very nicely for our needs here. So just don't forget that d dx tangent x equals secant squared x, and d dx secant x equals secant x tan x. So we'll take a quick couple seconds for you to copy that down, and then we will illustrate with an example. So here we go. Classic example. Tangent x to the 6th, the indefinite integral of tangent x to the 6th times secant x to the 4th dx. So let's take a look. First, we're going to start by splitting secant x to the 4th into secant squared x times secant squared x. So we get the indefinite integral of tangent x to the 6th times secant squared x dx, and then we're going to substitute in our trig identity. So we are going to get the indefinite integral of tangent x to the 6th times 1 plus tangent squared x times our secant squared x dx. And you kind of see where I've sectioned off in blue where it's going to work beautifully with our u sub. So u sub, u equals tangent x, du equals secant squared x dx, and you could probably see where this is going, where we have the indefinite integral of tangent x to the 6th times 1 plus tangent squared x times secant squared x dx. And here we go with our u sub, the indefinite integral of u to the 6th times 1 plus u squared du equals. And you can see what I did here. You could technically, if you want to, apply that over right here before you go into your u sub, you can. I find it's a lot easier to see it when it's just little u's, and then you can put them all back in later. So we distribute and we get u to the 6th plus u to the 8th, and then we integrate du, then we integrate, we get 1 over 7 u to the 7th plus 1 over 9 u to the 9th plus c, don't forget the plus c, equals, and this we're just going to substitute u equals tan x right back in, 1 over 7 tangent x to the 7th plus 1 over 9 tangent x to the 9th plus c. And that is complete, and I'll give you a little bit to write that down.
There's one step that I would like to illustrate that hasn't been written out here, and it's just that you need to distribute this u to the 6th, right, before we integrate. So when you distribute the u to the 6th, you'd get u to the 6th plus u to the 8th. And that's what we integrate to 1/7 u to the 7 plus 1/9 u to the 9. If we try to integrate before distributing, then this would be a u, but we know integrals don't play nice with multiplication, right? So we have to distribute that u to the 6th, then take our antiderivative, and that'll give us this. I think something that we're seeing in Sarah's notes, and that you'll notice as you go, so you start seeing these very quickly after you practice a few of them. They're quite nice.
And if you'll notice in that previous example here, I'll scroll back to it, these are even. Let's take a look about when they're odd. So the indefinite integral of tangent theta, here's one of our lovely rare theta examples, tangent theta to the 5th times secant theta to the 7th d theta. So we start by taking one off of each of these. So our tangent theta to the 5th becomes tangent theta to the 4th, and here's a regular tangent theta off to the side, and our secant theta to the 7th becomes our secant theta to the 6th, and a little secant theta off to the side, and hold on to that d theta, and we are going to split first our tangent theta to the 4th into essentially tangent squared theta times tangent squared theta, which can also just be tangent squared theta squared. So we can sub in some lovely trig identity right there. So we take all of this, and you can see I've already started to set that aside for our u sub. So we substitute in for tangent squared theta, secant squared theta minus 1, and don't forget that all of that is squared, times secant theta to the 6th times tangent theta to secant theta d theta, and we set our u to equal secant theta, since all of our terms except for that is now secant. And our du equals secant theta tangent theta d theta, which is gorgeous. So we end up with the indefinite integral of, you can see I waited to do that, just waited until it was all u's, u squared minus 1 all squared, u to the 6th du equals, and don't forget this is u squared minus 1 times u squared minus 1, equals the indefinite integral of u to the 10th minus 2 u to the 8th plus u to the 6th du. Let's integrate. Get 1 over 11 u to the 11th minus 2 over 9, don't forget that 2 right there, minus 2 over 9 u to the 9th plus 1 over 7 u to the 7th plus c, don't forget our plus c, and then we're going to substitute back in u equals secant theta, 1 over 11 secant theta to the 11th power minus 2 over 9 secant theta to the 9th plus 1 over 7 secant theta to the 7th plus c. And that is our final answer for that, and I'll give you some time to write that all down.
I have the same little notation comment here on several others. In the second integral, on the second line from the bottom, we want parentheses around that polynomial. That du, the differential, always acts on everything. And if we had to do a further substitution, we would need to think about it like that, like distributing whatever comes from the du or goes out. But yeah,
Thank you.
they're a lot of fun. Sorry, the magic here is that the derivative of secant is secant tangent. So if you want to sub for secant theta, you got to grab out a secant tangent, set aside. Sorry about the audio too. I don't know. I think I probably blew out the speakers on this computer by cranking it too loud. So it's, it doesn't seem.
So you can really just see here how we're just taking out little bits from each of these, and it's really making it just so much easier to integrate using the use of skills that we already have, and it's just kind of keeping in mind a few basic principles.
That's pretty damn funny.
So once again, let's look at that overall
Thank you.
format. So tangent x to the power of m times secant x to the power of n dx. So here's the general rules. If the power of secant is even, where n equals 2k and k is at least 2 or more, put aside one factor of secant squared x and use the identity secant squared x equals 1 plus tangent squared x on the rest of the factors.
This inequality.
So your equation, other than the secant squared x set aside, should be left entirely in terms of tangent x. Then do your u sub, u equals tangent x, and go from there. And if the power of tangent is odd, m equals 2k plus 1, put aside an m, again, we're referring to that exponent right up there. Put aside one factor of secant x tan x, and you remember how we kind of separated it out, so if it's not already a secant x tan x, you can pull one out of those odd numbers, and use tangent squared x, that identity, tangent squared x equals secant squared x minus 1 on the rest of the terms, so your entire equation, other than the secant x tan x set aside, should now be left entirely in terms of secant x. Then, do your u sub, u equals secant x, and integrate through from there. So I'll give you a little bit of time to write that down.
High-level strategy. If the power of secant is even, you're going to sub for tangent. If the power of tangent is odd, you're going to sub for secant. And then to make those go, use this middle trig identity right here. These are the next ones.
We will pause here and come back in the next video for the next little chunk.
Does anybody want to ask anything, either in the room or online? I feel mostly comfortable with what's going on.
What's the deal with like the
Suppose-
type?
So this is the book breaks this down in a very granular fashion. So saying if n is an even number, if the power of secant is even, what an even number is a multiple of 2. So saying if n is an even number, then it can be written in the form 2 times k, where k is some other integer. This should be greater than or equal to 1, I think, right here, instead of less than or equal to 2. But if n is equal to 2k, then you can set aside a copy of secant squared. You can set aside 2 copies of secant. And the magic is that what's left, if you have an even number of things and you set 2 of them aside, you'll have an even number of them left still, right? Because if you subtract 2 from an even power, you get another even power. So in case 1 here, if you grab aside and set aside a copy of secant squared, then you've reduced the even power of secant by 2, leaving you another even power of secant, which you can then rewrite in terms of tangents, because tangent squared plus 1 is secant squared, right? So if you have secant squared left over, it can be rewritten as tan squared plus 1. If you have secant to the 4 left over, it can be written as tan squared plus 1 all squared. In any case, you'll have stuff left over that you can turn into tangents using this identity. The case here in the book, if you look at it, they break it down in a very granular fashion. They show you, they replace secant to the n of x by secant to the 2k of x, and then show you pulling 2 of them over. So you have 2 times k minus 1 copies of secant left, and they show you how exactly what that replacement will come out to. But it's not especially necessary. So the way I would recommend thinking of this is if the power of secant is even, you're going to sub for tangent. And then you'll need to do trig identity work to make that substitution go. The power of secant is even, you're going to sub for tangent, which means you're going to set aside 2 copies of secant and then use the trig identities to make everything else match. If the power of tangent is odd, then you're going to sub for secant, which means you need to set aside a copy of secant x tangent x, because that's the derivative of secant. That's what your du will be. And then everything else that's left over, you need to rewrite in terms of the secant function. And again, that's this identity. So when you grab one tangent to make secant tangent out of your odd power of tangent, what'll be left is an even power of tangent. And that identity allows you to take even powers of secant and turn them into tangents, or vice versa.
So we looked at the power of secant being even and the power of tangent being odd. But what if the power of secant is odd and the power of tangent is even? So we will get to that in a second, but first just a quick note. There will be instances where you're going to be left with a single factor of secant x or a single factor of tangent x, and you're not going to be able to like get rid of it, finagly around it using the identities using those above methods. So for these, remember, you can still use the indefinite integrals of each. So just keep in mind what those indefinite integrals are, because you will come across instances where you will need to just use those. So the indefinite integral of tangent x dx equals the natural log absolute value of secant x plus c, and the indefinite integral of secant x dx equals the natural log of the absolute value of secant x plus tangent x plus c. So I'll give you a couple seconds to write that down, and then we're going to look at a quick example, and then we're going to move on to odd secants and even tangents.
The bottom ones are really kind of precise. It's a weird thing.
So here's an example. The indefinite integral of tangent x cubed dx. So as you can see, we start out separated into two pieces. We have a tangent x times a tangent squared x dx, and then we're going to use our identity right here. You can see I've highlighted that. So we have the indefinite integral of tangent x times secant squared x minus 1 dx, and then what we're doing is we are first distributing, and then we're going to split it into those two integrals in the way that we can, because integrals allow for that. So we have the indefinite integral of tangent x times secant squared x minus tangent x. So we end up with the indefinite integral of tangent x times secant squared x dx minus the indefinite integral of tangent x dx. So quick break for u sub, u equals tangent x. We're just following that general format that we had before. So u equals tangent x, du equals secant squared x dx. Moving right along, we get from this, this bit's already been taken care of with our u sub. We get 1/2 u squared because it just becomes the indefinite integral of u du. So we get 1/2 u squared plus c minus this bit, which we have not gotten to solve yet, minus the indefinite integral of tangent x dx equals, then we're going to substitute this back into this half, 1/2 tangent squared x, or you could even do it tangent squared x over 2, minus, and you can't mess around with this one any farther, so we're just going to put in the definite integral right there, minus the natural log of the absolute value of secant x plus c, and that's our final answer for that bit. So I'll give you a little bit to write that down, and then we're going to get to the just super special last problem.
So kind of in our collection of shit we need to have on deck for these, we can add those other tangents.
So, one final thing, and we can put this beast to bed. So this one's a doozy, but by now our brains are all nice and warmed up. We'll get through it. So what do we do when the power of secant is odd and the power of tangent is even? So this will require IBP's more quick to anger but easier to calm cousin, looping IBP. So make sure you have that skill set if you haven't gotten it super sharpened yet. So we'll work through one classic example to demonstrate how this works. I'll give you a second or two to write this down. So here's a lovely example. And it's a classic one that you might actually see elsewhere. So it's the indefinite integral of secant cubed x dx. So we start by breaking it into two parts, as we've been doing a lot this morning. So we get the indefinite integral of secant x times secant squared x dx. And we're going to do IPP. So select your u and your dv. Our u in this case is going to be this secant x, and our dv is going to be everything else that's left, the secant squared x dx. And calculate our du and our v. So our du is going to be secant x tan x. Dx, sorry, there should be a dx right there. And v is going to equal tangent x. So let's tackle this after I give you a couple of seconds to write. But don't forget when you're taking that note down, there should be a dx right there. Don't forget your terminology. So I've got this up here in the corner. This is our map key. So don't forget this is the classic format of integration by parts. This is our u, our dv, our du. It's still missing that thing, so don't have yours missing that, and our b. So here we go. The indefinite integral of secant cubed x dx equals, we've IPP'd it now, so it's secant x times tangent x minus the indefinite integral of secant x times tangent squared x dx. Now, we use a quick identity substitution. Tangent squared x equals secant squared x minus 1. So we get secant x times tangent x minus the indefinite integral of secant x times tangent squared x. And here we're going to do our substitution right there. So we get secant squared x tangent x minus the indefinite integral of secant x times secant squared x minus 1 dx. So you're going to see there's a little step right there, so you're wondering what happened. So first distribute, so you're going to end up with the minus the indefinite integral of secant cubed x minus secant x, and then you can split that into two separate integrals because that is absolutely allowed. So we get secant x tangent x minus, and keep those parentheses because you've got to keep that, whatever's inside of here, this is going to get applied to all of it. So keep those parentheses or brackets, whichever makes it clear to you. So minus the indefinite integral, open brackets, the indefinite integral of secant cube x dx minus the indefinite integral of secant x dx. And now we're going to apply that negative sign, so we get secant x, so that equals secant x tangent x minus the indefinite integral of secant cubed x dx plus secant x dx. Do you recognize this troubled young soul? Because that is exactly the same thing we started with, and that is our cue, which we will do after I give you a little bit of write it down, to start looping, because it is absolutely applicable. Cue looping. So secant cubed x, my bad, dx equals this bit that we just got over here, secant x tangent x minus secant cubed x dx plus secant x dx. So we will apply. So first we're going to break this down a little bit, and this is another one of those ones where you cannot, push it any farther. You're just going to bring in that indefinite integral of secant x dx. So we get the indefinite integral of secant cubed x dx equals secant x times tangent x minus the indefinite integral of secant cubed x dx plus the natural log of the absolute value of secant x plus tangent x plus c. And this is where we're going to bring in our basic algebra. So we're going to take this right out. So we get this plus itself, so it's just 2 times the indefinite integral of secant cubed x dx equals secant x times tangent x plus the natural log of the absolute value of secant x plus tangent x plus c, and then you just divide all of this by 2. So you can put a big old line and put a 2 under it, but it's just, I find it's a little tidier. Just like that, and we've used looping IBP. So I'll give you some time to write that down.
This is all the pieces are coming from. It's a little weird. It's nicer than the other looping integral, right?
And that is
Well,
it.
not
So
DP.
if you have any questions, feel free to ask. But yeah, I should be here on Zoom. So yeah, feel free to ask any questions. And thank you so much for listening.
I'll go ahead and stop the video there. First, definitely want to thank Sarah for all the work she put into this. Not a small amount of effort. Nicely recorded videos, very, very lovely done. And I appreciate the sense of humor you have in this stuff. I think that really does help. The office reference was particularly enjoyable for me. Does anybody have any questions about those integration techniques? A couple things I do want to do, especially we have about 10 minutes before class needs to end. I want to summarize really quickly the strategies. I think it's nice to have those in one place. It's not. So I'm going to bring up the lights here, pan over. The first thing that people online may or may not have seen. Just some necessary stuff for this section, right? The trig identities that we use, I bet this in the right spot here. The trig identities that we use are on the far left. These are the necessary ones, and you'll hear me refer to them by name. The first trio here, I'll call Pythagorean identities, because these are all really consequences of a squared plus b squared equals c squared. Sine cosine integrals, if one of the powers is odd, we use this guy, right? Or one of his other forms, like cos squared equals 1 minus sine squared. Secant tangent integrals, where the power of secant is even or the power of tangent is odd, both use the second Pythagorean identity. And then you could see cosecant cotangent integrals. And the rules for those are exactly the same as secant tangent integrals, but you need to use this Pythagorean identity that relates cosecant to cotangent. And then the two half angle identities, we use these anytime you're integrating a power of sine times a power of cosine, and all of the powers are even. The micro U subs that we use in this section most commonly are the top two here, right? The sine AX and cos AX integrals. Each of these come from just substituting like z equals AX. dz would be a dx. So you get a 1 over a up front, and this will turn into the integral of sine z dz. Integral of sine z is negative cos z. So the 1 over a, negative cos, and then z is AX. So those two are the micro U subs that we use a lot. I'll call it a Z sub. It's worthwhile going through the process of actually plugging this in once to see that it comes out that way. These guys are technically both Calc 1 integrals, but I think probably a lot of people have never seen the secant integral done. So I want to show you where each of these come from. These are both U sub things. You do want to just memorize both of them, right? Like you know the integrals of the other trig functions. We should know the integrals of secant and tangent. It should just be like right there in our list of known antiderivatives. The tangent one, I'll show you really, really quick. It's not hard. The secant one requires a bizarre creative step. Integrate tangent. You write it as the integral of sine over cosine. And then in this expression, we sub z equals cos x, which means dz is the negative sine of x dx. And when you plug that in, sine of x dx is negative dz, so you get a negative here, and then 1 over cos x is 1 over z. antiderivative for 1 over z is the natural log, so this is negative natural log absolute value of z plus a constant. And then z is cos x. So you get negative natural log absolute value of cosine. And that's not looking like our answer over there. So what's going on?
Can you take away the negative and make it 1 over cosine?
Yeah, exactly. So the power, sorry, the multiple in front of the logarithm, that was a rule for logs. This is multiples out front, we come inside as powers.
Oh, yeah.
So if we do that here, we're going to get the positive natural log of absolute value of cos x, the negative first, which is not the inverse cosine function, right? Not arc cosine, but it's the actual power. So it's 1 over cosine x, which is secant. And because secant and tangent are connected to each other, through the normal way of writing derivatives, I think it's much nicer to think of this integral as the natural log of secant rather than negative natural log of cosine. But either one is correct. Either one is fine. Most people just prefer to remember it like this because these secants and tangents show up together all over the place. They're buttons.
Is there a difference between writing the -1, like say, like right in between the cosine and the x versus like after the x?
Yes. So a few different places that could show up, right? The thing that we're doing here,
Yeah.
that's 1 over cos x, which is secant x. Certainly this is different than this, which generally stands for the arc cosine function, like the inverse cosine function. And these are different.
What about like right after the x?
Yeah.
Like outside of the parentheses though.
Oh, so the last place I was going to put it was here. And this would be cosine of 1 over x, which is different. If you put it outside the parentheses, then that would be the same thing as this. But I would argue that that's the notation that we should stay away from because there's some ambiguity to it. So yeah, different ways to kind of do things with -1 powers and cosine. Here we're talking about this one. The secant integral is much weirder. So while I have you captive for just a moment more, has anybody ever seen this one?
I don't think so.
I don't think so. Yeah, it's technically a Calc 1 problem, or it's attackable in section 5.5, just like the tangent integral is. But the reason it's so rarely seen is because there's a bizarre creative step. Now, I can multiply by 3 over 3 or 5 over 5 as I want to, to create a common denominator and do stuff like that. Here's the strangest version of that which you will ever see. I'm going to multiply by secant x plus tangent x over secant x plus tangent x. Why? No reason. Because I can. Because this is 1, right? Because I'm multiplying by 3 over 3. The magic is that when you distribute, right, secant x is secant x over 1. So the 1 times the downstairs stays the same. Upstairs, you get secant squared plus secant tangent. And it's totally reasonable to be like, why the fuck did you do that? Stare at the top for a minute. Stare at the bottom for a minute. What's the derivative of secant?
Secant x tan x.
And the derivative of tangent?
Secant squared x.
Where? So the derivative of the bottom is the top. So this going to be so. 3 equals x plus tangent x and our dz is going to be all right, the substitution. So you sub to the bottom. So the derivative of secant is secant tangent plus the derivative of tangent is secant squared. So the differential is all of that in parentheses times dx, which is the top. Right, so in the other order. This becomes the humble one over z integral, just out of nowhere. It's very, very strange. There are other ways to do this. After I teach you partial fractions, there's a trick doing kind of an infinite version of partial fractions that we'll get here. But I'm genuinely not aware of any nice way, like that doesn't involve some sort of what the hell step to integrate the secant function. Odd powers of secant are just gnarly. They are, right? That last problem we saw, secant cubed, secant to the fifth, secant to the seventh, any odd power of secant, including secant to the one, is gnarly. So, let's see. Nobody wants to go through this every time you encounter the integral of secant. It shows up all the time in those problems, so you need to just remember these four. All right, these are things that you want to just have ready and available to go without cooking them up. The other thing I want to say before I let you go, and this will be the last, there will be a looping integral on the exam, right? My exam one in this class always has a looping integral. Usually there's an element of choice, like pick one of, cosecant cubed 2x or e to the negative x sine 3x, something like that. So practice the looping integrals. Practice.
We can take an integral.
Usually that's how I write that
So
problem.
there's like here when you choose one for the problem.
The last few times I've written that test, that's how I put it. Yeah, and odds are I will do the same this term.
And is the study guide gonna go out?
We're getting kind of close. Yeah. So where are we with respect to the test? We need to get through 7.4 before I can publish the study guide. 7.4 is partial fractions. Today's 7.2. Next time we'll do 7.3, which is trig sub, then 7.4. So today being Monday, probably I'll finish 7.4 on Friday, which means the study guide will go out Friday, exam probably 1 week from this Friday. But I'll talk more about that when we get a little closer. Any questions from my folks online?
All good here.
Oh, could you
Right. Thank God we're going back to the normal shit. Okay.
make it faster?
Alrighty, gang. I will see you all on Wednesday then, when we will talk about 7.3, which is trig sub. That's where you take integrals that don't have trig in them and make them have trig in them. So you want to practice these ones before then. I'll post a homework set for you. I have another class immediately after this, but as soon as I finish that, I'll post your new homework set. So homework should be up before 2 p.m. Take a look at least one or two of those problems before class on Wednesday. That way you will not be lost, because on Wednesday we're going to be doing